This physics video explores the concept of uniform motion. Now, uniform motion is pretty much what it sounds like. It refers to an object moving in a consistent or uniform fashion, but we should be specific. Like, what is it we observe to describe motion, and how can we determine if this motion is uniform? Well, when an object changes its position, it experiences motion as it travels a distance or undergoes a displacement. So we'll define displacement as a change in position. We denote this change with the Greek letter delta followed by some letter x or d or whatever variable makes sense in a given situation. For now, let's just use x. Now, mathematically, we take our final position with respect to some common reference that we often call an origin and subtract our initial position. This difference is how much the position has changed, our delta. But how can we assess how uniform that motion is? Well, if the motion is consistent, it would look the same at different times. More specifically, we'll use the rate of this change in position over an interval of time that we'll write as delta t. This rate, that we'll refer to as speed or velocity, is found with the expression delta x over delta t. Now, if the rate remains constant, it'd be fair to call this uniform motion, yeah? But there are other things that could be uniform and still pertain to motion. For example, if the object remains in the same position for a time interval, that would be uniform, but it wouldn't be considered motion. And mathematically, since the initial and final positions are the same, the delta is zero, which again is consistent with no motion. And likewise, if the velocity changes or accelerates in a consistent way for a period of time, this could also be considered uniform. But for the sake of convention, we'll only consider objects moving with constant velocity to be in uniform motion. And at the risk of spoiling the vectors video, another component of velocity, other than the rate of motion that remains constant in uniform motion, is the direction of travel. So both the speed and direction must remain the same to qualify as uniform motion. So let's consider a motorized car moving in a straight line along a hallway floor. If I video it for 5 seconds and notice it moves 2.4 meters in the first second, then 2.4 meters in the next, and the same observation is true for each 1 second interval, it would be fair to say that the car is moving with uniform motion, because based on the stated convention, this fits the mold. Both the rate and direction appear to be constant. And we can look at the math to confirm this. Let's calculate the speed of the car for the first second. The convention is to use v as our variable for speed. So v equals delta x over delta t, which is 2.4 meters divided by 1 second for a speed of 2.4 meters per second. The calculation is the same for the final second. Interestingly enough, if we take the total distance and the total time and calculate the speed for the whole trip, we get 12 meters or 2.4 meters times 5 divided by 5 seconds. And again, the speed is 2.4 meters per second, a uniform result. Now let's take a ball and toss it in the air. If we use a slow motion video to get time and displacement information, we find that it leaves my hand traveling 4 centimeters in 1 frame advance. And according to the camera spec, the time between frames is 1/60th of a second. If we fast forward to the end of the video, we notice that just before I catch the ball again, what do you know? It travels 4 centimeters in the last frame advance. Now at first glance, the motion looks like it could be uniform, but a quick review of the data reminds us that the ball was going up in the first frame, but returning downward in the last one. So the rate might be the same both times we looked, but the direction wasn't. But if we replay the ball's entire trip in our mind's eye, we realize that even the speed didn't remain the same. It slowed down as it traveled upward until it reached the top of its flight, where it changed direction and proceeded to speed up on the way down. Definitely not uniform motion. And finally, let's consider a stone tied to the end of a string and swung in a horizontal circle. We do this under a bridge, and from on the bridge, use a slow motion camera to record the flight. And again, we look at the video. This time, every time we advance 1 frame, the stone is exactly the same distance from the previous frame, but the direction is ever so slightly different than the last advance. So we compare this to our definition of uniform motion. And while the speed appears to be the same, after all, we have the same distance and the same time interval in each frame advance, that pesky direction keeps changing. So it looks like a thumbs down to uniform motion. But as science has done over and over throughout its history, when observations don't fit the working understanding of things, it's time to either rework the observation or revisit the model. Now it sounds like we've got some work to do, so let's get moving.